The title of the first paper is Attention-Based Relation and Modeling for the Point Cloud Semantic Segmentation. The authors are the Ziyu Hu.
你会的语言真多。如果你希望我
and the Dongbo Zhang, Shuai Li from Beihang University, and the Hong Qing from Stony Brook University in the US. So the work today will be presented by the Ziyu Hu from the Beihang University. So can you please share your screen and please start?
Yeah. Can you guys hear me?
Yes, very clear.
Okay, I'll start now. So hello everyone, and first I will thank you for Professor Huang for the introduction. And I'm Zhiyu, I'm from Beihang University, and I will present our paper, Attention-Based Relation and Context Modeling for Point Cloud Semantic Segmentation. Semantic segmentation of point cloud plays an important role in scene understanding and has shown extensive usage in many downstreaming applications, including robot, autonomous driving, virtual and augmented reality, etc. Although recent works have achieved a remarkable success, fine-grained point cloud semantic segmentation is still challenging to the research community, given the fact that the point cloud is usually unstructured, unordered, and sparse. And therefore, the method must hold the property of permutation invariance and has to be robust to sparse, partial, and large-scale data, which is not easy to deal with. To overcome these challenges, a wide variety of approaches have been proposed, and the pioneering works are the famous PointNet family. And based on PointNet family, a lot of neural network architectures have been proposed. Considering the focus of our work, we will divide them into two categories: point relation learning methods and point context learning methods. First, we will introduce point relation learning methods. Using PointNet as its backbone, Dynamic Graph CNN proposed an edge-conf operation to dynamically pull features for a target point from its neighbors in the manner of a weighted sum. And PointCNN proposed a XConf operator to learn a transformation matrix and simultaneously weight and permute the input point features to overcome point ordering issues. And based on PointNet++, RSCN learned feature weights from extracted spatial information to get shape-aware representation. And GeoCNN models geometric structure between points via vector decomposition. And context modeling is important for semantic segmentation task. By exploring the proximity of certain point to other points in semantic space, semantically correlated information can be harvested even if points are far away from each other, while irrelevant information can be suppressed even if points stay close. Shape Context Net learns local context in 3 steps, similar to PointNet++. And Point Edge learns point local context by adding an edge branch to the original PointNet++, which explored the semantic similarity between points and is under very strong supervision. ELGS applied spatial and channel attention on point cloud to learn global context for each point, which brought about considerable computational cost. Now we will briefly introduce the pipeline of our method. We handle point cloud semantic segmentation by a hierarchical encoder-decoder architecture, which is based on PointNet++. For the encoding part, our relational encoder attempts to learn the semantic relation between neighboring points with the interaction of all the points in local neighborhood. And for the decoding part, our contextual decoder flexibly captures long-range dependencies between points even far away in spatial location. And besides, we adopt a gated propagation strategy instead of skip links between the encoder and the decoder to flexibly filter out irrelevant and redundant information. So given the 3D point cloud as input, our encoder first downsamples the input points by Fawcett's point sampling. And after that, our decoder upsamples the points gradually to its original resolution. For each sample point in encoder, we utilize ball query to find the neighbors of the point which form a customized local neighborhood for this point. Each local neighborhood has up to 32 points. As you can see, the radius of ball query is gradually increased as the point number is gradually decreased. So this is the network architecture of our method, which mainly consists of local relation learning modules, gated propagation modules, and context-guided aggregation modules. Our network is trained end-to-end and guided by the multi-scale laws. I will explain each module in detail in the next several pages. So our local relation learning module consists of two submodules, spatial information extraction and cascaded attention-based pooling. For each local neighborhood centered at a certain point, say PI, we learn the relation between PI and its neighbors from local spatial information. Specifically for PI and one of its neighbors, say PJ, we follow RSCN to explicitly create a 10-dimensional vector Hij. Such a 10-dimensional vector explicitly contains the spatial and geometric information so that the relation between PI and PJ can be implicitly encoded by MLPs. The MLPs maps Hij to high-level features with a C1 dimension, and we concatenate these features together, which is then concatenated with the point feature with C2 dimension to get an enhanced feature, which is of a C1 plus C2 dimension. Suppose there are K points in the local neighborhood of PI, in which case the enhanced feature can be expanded to K rows with C1 plus C2 columns when all the points in the local neighborhood are considered. To generate attention weights for K points, the expanded feature is first passed through an MLP layer and get transposed. Notice that here we deliberately transfer the expanded feature from C1 plus C2 to C2 dimension to maintain the original dimension of point feature. Then we apply softmax operation to it so that attention weights for K points add to 1. After that, element-wise multiplication is performed on the feature and the attention weights, which gives us a reassigned feature. It is worth mentioning that this attention-based feature reassignment allows the reinteraction between points and thus captures richer information. We duplicate this process to better learn the feature distribution of neighbors and guarantee adequate interaction between points. At last, we pool the features by summation to get the output feature, which is the customized local feature for the point PI. And inspired by the non-local neural networks, we leverage a similar structure to model the context. Instead of placing the context-guided aggregation module after the last feature propagation layer, we integrate these modules into the early layers of the decoder, which is of a lower resolution, such that the computation and memory consumption can be largely reduced without sacrificing the performance. So given an input feature with endpoints and C-dimensional features, we first apply 1x1 convolutions to transfer the input feature to different embeddings Q, K, V, which denote query, key, and value respectively. Then K is transposed and left multiplied by Q to get the affinity matrix which is of n times n dimension. Then we apply softmax operation to the finite matrix to calculate the attention weights. And finally, we perform matrix multiplication on the attention weights and value V to aggregate contextual information from value points for each query point. And it gives us the augmented feature, which will be fed to the next feature propagation layer in the network. To further suppress irrelevant information flow between the encoder and the decoder, we introduced the gated propagation module into the feature propagation layer, which aims to seek a balance between encoder features and decoder features before fuse them together. For input feature F encoder and F decoder, inverse distance weighted interpolation is first employed to interpolate F decoder to the equal resolution with F encoder so that we can concatenate them together. And after that, we successfully apply ReLU activation, 1x1 convolution, and the sigmoid function to the concatenated feature to get the balancing weights, which help balance the two features. After the balancing step, we concatenate these two balanced features together to get the output feature. As for the loss function, we use multi-scale cross-entropy losses to facilitate the training process. We conduct experiments on two public benchmark datasets, ShapeNet part and the Stanford 3D indoor scene dataset. Here are the visualization results of part segmentation on ShapeNet part dataset. And as you can see, our method segments these shapes very well. And here are the quantitative results of part segmentation on ShapeNet part dataset. We calculated part averaged intersection over union as the evaluation metric. As you can see from this table, the performance of our proposed method achieves comparable results with the state-of-the-art methods. Specifically, we achieve 85.8% PIOU, which is 2.1% and 0.7% higher than PointNet and PointNet++. So here are some visualization results of semantic segmentation on S3DIS area 5. Our method segments the input scenes with high quality, even in complex scenes, for example, office and conference room, which manifests the effectiveness of our method. As you can see in the circled places, compared with PointNet++, the results produced by our method are much more accurate and consistent, especially for categories like door, sofa, table, and clutter. And here are some quantitative results of semantic segmentation on this data set. For the evaluation matrix, we use overall point-wise accuracy, mean of class-wise accuracy, and mean of class-wise intersection over union. And compared with the state-of-the-art methods, ours yields the highest score in terms of OA. Specifically, we achieve 88.5% on OA, which surpasses all previous methods. And besides, we achieve 66.09% and 59.66% on M accuracy and MLU, respectively, which is on par with these approaches. And to further demonstrate the capability of our method in terms of enhancing the point's representative power in feature space, we present the TSNE visualization of learned features. From the left to the right are visualizations of input features, features learned by PointNet++, and the features learned by our method. We can observe that the features learned by our method are much more discriminative than the PointNet++ counterparts. And to quantitatively measure the discrimination of the learned features, we designed two metrics, the inter-class distance and the inter-class distance. And from this table, we can see that our method achieves higher interclass distance and a lower intra-class distance than the PointNet++, which means that the features learned by our method are more discriminative and compact. And to verify the efficacy of each module in our framework, we conduct ablation studies. We unload each module from our full pipeline and compare the performance with and without each module. As you can see in this table, our method improves the performance over the PointNet++ baseline by a large margin. And after removing each module, there are performance degradation of varying degrees. We can see that the degradation is worst when the local relation learning module is removed. And although our proposed method achieves decent results in point cloud semantic segmentation, it still suffers from several limitations. As a supervised learning method, our method fails to handle the model of unseen category in training stage. For the survival between the seat and the base, our network wrongly predicted as armrest. And for the lamp model, our network habitually as a base part. Besides, our prediction is still imperfect when it comes to thin and sparse structures. In summary, we presented a novel hierarchical encoder-decoder architecture to do the point cloud semantic segmentation task. And different from the existing methods, our method can adaptively explore semantic relation between points by incorporating our local relation learning module. And moreover, we proposed a novel multi-scale context-guided aggregation module to further capture long-range dependencies. And a gated propagation strategy is adopted to replace skip links with the aim of filtering out irrelevant and redundant information. Extensive experiments and comparisons on public benchmarks have shown that our method outperforms the baseline method significantly and achieves competitive results compared with the state-of-the-art methods. And currently, our pipeline is still not quite lightweight enough to perform scene-level semantic segmentation in real time, which might impede its industry-level applications. So in the future, we would like to further reduce the complexity of our network architecture to achieve better efficiency without sacrificing the performance. In addition, we also plan to extend our framework to fine-grained object part segmentation and instance-level scene semantic segmentation. And we would like to thank these grants and funds for supporting this research. And that's all. Thank you all for your attention.
Okay, so thanks to you. So as you can see from this chat, so there already has a questions for you. So can you answer it?
I'll check that.
Yeah, can you see the chat window?
Yeah. Could you elaborate on the degree to which your method is dependent on the resolution of the models? That is, what would happen if you pass different resolutions of the same model to the method? Would you find the same features in all of them, or would the features differ from the resolution? So let's see. So the question is that what if the resolution of the models is different? Will the features learned by our method differ? I would say the features learned by our method won't be exactly the same, but the distribution of features learned by our method will be similar. For example, if you in our framework, the resolution of the model from left to right are 1024, 256, 64, and 16. And decoder, in our decoder, the resolution is gradually increased, vice versa. And I think the resolution doesn't count that much because we learn the feature distribution of points rather than a single point, the feature of a particularly single point. So does that, so I don't know if my explanation can get you across.
And also there has, I think also is the related question about this, I think.
Oh, let me
Can
see.
you take a look?
I'm curious about the design of multi-scale architecture. Have you tested your network with different scales? Does the performance become better when the scale number increases? The question is similar to the above one. So in our multi-scale loss, the I'm not sure your question is about the loss or the architecture. Different scales, different scales. We didn't test our framework with different scales, and the scales we use are inherited from the .NET++ baseline.
Yeah, his question is about this multi-scale architecture.
Okay, I think I answered that.
Okay, since it's already like 2 minutes past, so due to the time limit, so we have to move to the next talk. So I think the later, if you have more questions, we can certainly reach out later. Okay, so let me introduce the next presentation is about the vectorization of the persistence barcode with application in pattern classification of Puros structures. So the authors are the Zhe Tongdong, Chuanfeng Hu, Chi Zhou, and Hong Weilin from the Zhejiang University in China. So the work today will be presented by the Zhe Tongdong. So can you really share your screen and start? Yes.
Okay, can you hear my voice?
Yeah. Can a little bit louder?
Okay. And now it's okay?
Okay.
Okay, hello. It's our honor to present our work about the vectorization of persistent barcode with applications and in part classification of porous structure in this international conference. The work is authored by Zhe Tongdong, Chuanfeng Hu, and Chi Zhou, and supervised by Professor Hong Weilin from School of Mathematical Sciences, Zhejiang University. And this work is supported by National Natural Science Foundation of China. Considering the audience is not familiar with persistemology, we will give a brief introduction. And we focus on the methods of vectorization of persistent barcode and the applications of porous classification. Persistent homology is an effective tool for obtaining topological features of spatial objects. It has used to discover the topological patterns of practical data in recent decades. persistent barcodes is the summary of topological features. The extracted features are potential to be used in machine learning tasks, such as classification. However, because the number of pairs in barcodes is not fixed, and it is not straightforward to compute the similarity of persistent barcodes, barcodes cannot be directly used in machine learning tasks. Therefore, the problem arises to transform persistent barcodes into the representations compatible with machine learning tools. So our aim is to vectorize persistence barcode, and we propose the principles to design the representation of barcodes. The representation should be explainable, and it should preserve the information of barcode. And it's better to be stable, which means small change in the barcode leads to the relatively small change in the representation. And the vectorization representation is used for classification of porous structures because the topological features matter in porous models. And in this paper, we propose a finite and dimensional vectorizing representation of barcode based on Hart-based decomposition of persistent rank function. And we prove the stability with respect to one Waterston distance of barcode. And the proposed vectorizing representation is applied to classify a novel data set of porous materials and has the best performance compared with other vectorizing methods. Here, we give a brief introduction of persistent homology. One of the purpose of persistent homology is to infer the essential topological features hidden in a given point clouds with noise. And given a point cloud, an open bore assigned on each point with a variable radius, a simplicial complex is obtained by considering the intersection of open bores. The different rules of considering the intersection lead to the different complex. In this figure, it illustrates Czech complex. As the parameter, that is, the radius increases from 0 to a large number, it gives a nested complex sequence, which is called a filtration. And as the radius increases, new topological invariants, such as holes in different dimension, appears, and they disappear as some high-dimensional simplex emerge. Intuitively, see the figure. The values of the parameter at which the topological invariants appear and disappear are recorded as an interval, which represents its lifespan. The intervals are orderly exhibited in the plane as a barcode. To measure the similarity of barcodes, the p-Waterston distance is provided in the following equation. By setting up a matching between two barcodes and finding the infimum of total differences of paired and unpaired intervals according to the matching. And it is approved to maintain the stability that small changes in the data imply at most small changes in the barcode. Here, we introduce the main method of our paper. Due to the principles to design the representation, we used a proper transformation of barcode, which is a persistence rank function, shown in the figure. Intuitively, each bar in a barcode relates to a triangle above the diagonal. The function is meaningful. At the coordinate st, the integer value is exactly the persistence Birdie number, the persistent Birdie number, which means the number of k-dimensional holes existing in a parameter interval from S to T. To extend the persistent rank function to a limited rectangular domain, the extended PRF is defined by making the original PRF be symmetric with respect to the diagonal. In the limited domain, we consider to decompose the extended PRF by a series of higher bases because the PRF is a non-negative, piecewise continuous integer-valued function. And we propose the novel vectorizing representation here. Given the order of the base functions, the feature vector consists of the coefficients of each higher base function. Here we attach the algorithm to generate feature vector. First, to generate the discrete, First, to generate a discrete extended PRF. Secondly, to generate a discrete 1D higher base. Finally, to generate 2D higher bases in the form of tensor product, and to compute the coefficients as the entries of the vector. As we noticed that the obtained vector usually has a high dimension. For example, for fast computing, we set n to be 5 in our experiments, and which means to produce a vector with its dimension 1024. For those higher dimensional vectors, to prompt the training process of classification, we employed the technique of dimensionality reduction to produce lower dimensional vectors. Theoretically, we proved that one Wasserstein stability holds in some Mite conditions. That means small change in the barcode implies small change in the vectorizing representation. As the equation shows, in the condition of a small perturbation, the change of vectors can be controlled by the multiplication of the change on barcodes and constant. In experiments, we evaluate the proposed vectorizing representation on 11 datasets and compare the methods with 4 competitive vectorizing tools, which includes 3 kernel methods and persistence images. And we employed SVM classifier and other 3 classifiers. The technique of dimensionality reduction out of sample mapping in supervised manifold learning is used to obtain the lower dimensional vectors. On 7 datasets, the method without dimensionality reduction performs the best. And we find after dimensionality reduction, the accuracy on SVM classifier drops. Therefore, we evaluate the DR layer with ablation study. So DR layer preserved or even improved the classification accuracy on logistic regression classifier and the KNN classifier. As for time saving, after DR process, the total time cost of classification is reduced by 5 to 15 times. And the DR process can save time of training the classifiers, especially on large-scale data sets. Well, we now introduced an important application in the paper. To extract the informative patterns from power structures is a very important and a novel problem for material design. The porous model dataset is generated by using a triplet periodical minimum surface in B-spline solid. For training data, there are 9 types of TPMS, and the 3D surface can be sampled to be point clouds. And then the barcode is computed, and they are vectorized by the proposed method. Optionally, we use the dimensionality reduction, and the vectors are fed into the classifiers, and we use cross-validation to choose the parameters. For test data, we sampled 405 samples from B-spline solid models. The data are also transformed into the vectorizing representations to test the classifiers. The accuracy and the time costs are listed in the table. The proposed method with DR on SVM classifier achieves the best performance, and it costs less time than kernel methods, that is PWGK, PSSK, and SWK in the table. And the kernel methods cost so much time in training and testing because it costs a large amount of time to compute the kernel metrics. More hard-based functions are adopted to produce the feature vectors, and the accuracy remains high, about 80.6%. Therefore, the proposed method performs the best in this classification task compared with its competitors. To summarize, in point cloud classification, deep learning methods such as PointNet usually have stunning performance. However, the interpretability is the problem. The ML kernel methods have supportive theoretical guarantee, but it costs a lot of time in practice to train the classifiers. The proposed method is explainable, theoretically stable, and has nice performance in practice. However, the simple connection of all layers might cause the reduction of generalizing power of the pipeline. However, we think the proposed representation has potential use as handcrafted features or topological descriptors, especially for the scientific problem of discovering new porous categories on the real-world materials. And finally, we sincerely thank the audience, and any questions are welcomed. Thank you.
Okay, thanks, Tong. So, and okay, there has the question. Can you see from the chat? So, have you tested your method on the real data?
Yeah, we will use our method in real data, but in the paper we use the generalized data sets. For example, in the classification task of porous structures, we made the porous data sets.
Okay, so any questions? It looks like we can only take one quick question.
Yeah, I have a question. How have you compared your methods to other vectorization of persistence diagrams, like, for instance, persistence images or vineyards?
Of course. So can you see the tables in the PPT?
Uh-huh.
So we prepared our method with 3 kernel methods and the persistence images.
Okay,
So-
okay. Oh, good. Thanks. Yeah. Oh,
Okay,
actually, can I ask one other quick question about
Sure.
your stability result?
Of course.
The constant on that inequality is looks like exponential. How does that compare to other standard stability results? It looks like 2 to the power L or something, right?
Sorry, I cannot catch you.
The stability result,
Okay.
one
the
Wasserstein distance.
Okay, I know. So here,
Yeah, so
So
the constant on the inequality is 2 to the power 12 plus 1, right?
yeah, it's related to the largest number of the interval content
Okay.
in a barcode.
Okay.
So it's actually, it is a constant.
Okay. Thanks.
Okay, thank you.
Good talk.
Okay, thanks to Zhetong again. So now we'll move to our last talk of this session, which is the cross-domain retrieving sketch and shape using cycle CNNs. So the authors are the Minjia Chen and Changbo Wang from the East China Normal University and Li Gang Liu from the University of Science and Technology of China. So the work will be presented today by the Minjia Chen. So now, yeah, now he's ready.
Can you hear me?
Yeah, sure, clear.
Okay, so I will start our presentation. Hello everyone, this is Mingjia. I'm very glad to be here to present our work, cross-domain retrieving sketch and shape using circle CNNs. As we know, cross-domain retrieving has been a highly relevant and challenging research topic in computer graphics for the last decades. Especially the recent popularity of consumer electric device, multiple mode data such as image, video, and the 3D model has been widely available on the internet, which is the fundamental component to understand the real world. More specifically, the sketches by hand provide a convenient and efficient way to understand, to visually record and present 3D real world. They are rich enough to specific shapes. The goal of cross-domain retrieval sketch and shape is to allow non-artist users to draw visual content and then find matching examples in a shape collection, or allow users to search sketch for a given query shape in a sketch dataset. Recently, the dramatic
Hi, Minjia, can you hear me? Hello? Minjia, looks like we didn't hear your sound. Oh. No. But you can hear me, right? So or I don't know how. Yeah, maybe you can you try the other microphone or the better network? Okay, sorry for letting everyone waiting. I think she'll come back soon. Yeah. Can you see something? Looks like we cannot hear you. Okay, Minja, we can see your screen. We can see your screen, but we cannot hear you. I don't. Okay, now. Okay, now I can hear you.
Oh, okay. Okay, so I continue my presentation. So traditional methods directly project the data of different commodities from their own space into one single common feature space, where the Euclidean distance of features directly correspond to the semantic similarity between sketches and shapes. And this method appears dramatic, but it also brings a number of puzzling issues. For example, a shape often co-occurs with its corresponding sketches from different views. Thus, constructing one common feature space to treat different commodities equally would lose exclusive and useful commodity-specific properties, which cannot fully exploit the intrinsic information within each commodity. Considering the above issues, arise when we struggle to seek the common feature space for retrieving. In this paper, we demonstrate that by learning mapping between different feature domains, and we no longer require the seemingly indispensable common feature space construction. Traditional cross-domain retrieval approach follows the rending retrieving pattern, which first take advantage of rending method to rend the 3D models into 2D line drawing images and then compare them with a sketch query image. However, the rendering process needs to be done from multiple viewpoints about the 3D model to gain rotational invariance. Lately, deep learning methods has made great advance in multi-mode applications, including image video classification and object recognition. However, it requires explicitly construct the common feature space. So in this paper, we propose a new circle sequence which can construct the cross-domain mapping between the feature space of 2D sketches and the one of 3D shapes. The core of our method is that the mapping relationship can directly generated through the end-to-end framework without explicit common feature space construction. And our architecture can guarantee that the modality-specific characteristics could be fully explored. Now I will give more details about our cross-domain deep learning method. We start by overview our method. It is a composition of two feature extractors, 2D sketch feature extractor and the 3D shape feature extractor. Then to learning the cross-domain mapping between the feature space of 3D shape and the one of 2D image, we design a novel circle convolutional neural networks. We first show the learning process of 2D sketch feature extraction. For this extractor, we use the IXONet to encode input sketches. And this image encoder aims to extract a content-aware representation capturing an automatic content of input sketch. Furthermore, this encoder is learned by minimizing this energy function, and that is combined with classification process. The representation network of 3D shape is defined as a multi-wheel convolutional neural network. We use the definite architecture first proposed by Su et al. To encode the 3D shapes into the feature space. This network is trained as a part of classification task. Given the above extracted vectors, our aim is to set up the mapping functions between the feature space of 3D shape and the one of 2D sketch. Our circle CNN is composed of two networks, G and F, which share the same architecture but not parameters. Our mapping function G and F are a pair of reciprocal functions. The first one, G, computes the mapping from sketch feature space to shape feature space. And the inverse mapping function F aims to start from the shape feature space to sketch latent domain. The detailed architecture of our circle CNN is illustrated in this figure. We also designed a novel loss function to train our circle CNNs. The energy function is defined as follows. Consistent loss is known for the effectiveness to constrain the network to produce stable results. And our aim of cross-domain transfer is to ensure similarity between the mapped feature and the target one. So toward this end, we also design a similarity loss function to metric feature similarity using L2 normal. And we also design a classification loss. And this term applied to both mapping functions G and F between the sketch feature space and the shape feature space. Here we train each network separately rather than in an end-to-end manner. We first train those two feature extractors by using the defined loss functions. And then the cross-domain mapping network circle CNNs is learned by using those pre-trained feature nets. Now I will show several experimental results. We first show the effectiveness of our network on cross-domain retrieving 3D shape and 2D sketch. We can see that our method performs well in popular classes. And to illustrate the discriminative power of our method, we further show some statistics on TSP dataset using two criteria, precision record and precision protocol. It is interesting to see that our proposed circle CNNs works well on both sketch-based shape retrieval, the first table, and shape-based sketch retrieval, the second one. We also compare our cross-domain retrieval technique with the state-of-the-art methods on public benchmarks. The quantitative comparison results of sketch-based shape retrieval task are shown in this figure and this table. And we can see that our method is still superior than existing state-of-the-art techniques. And we also quantitative measure the performance of our method using the feature map. More specifically, we use TSNE technique to embed the sketch and the shape features from our sketch feature space into a 2D space. As shown in this figure, good matching sketches and shapes are also located as close as possible. And this feature map suggested that the usefulness of our circle CNNs for cross-domain retrieval. And we also get more results of our method on cross-domain retrieval and within-domain retrieval, including sketch-based shape retrieval, shape-based sketch retrieval, and within-domain shape retrieval, and within-domain sketch retrieval. In conclusion, we present a novel circle CNN that can be used for cross-domain retrieval of 2D sketch and 3D shape. Our method focuses on the main challenge, learning the mapping functions between the feature space of sketch and the one of shape. In terms of limitations and future work, first, we ignore the impact of different viewpoints for the final retrieving results. And second, it would be interesting to study better training strategies of circle CNNs, which can train the whole network in an end-to-end manner. And finally, we would like to thank our anonymous reviewers for their suggestions and our funding agencies. And thank you for your attention.
Okay, thanks, Minja. So now we can ask questions. Okay, so maybe I can ask one first. So actually, in this limitation, you just mentioned that like you actually ignore this you ignore the impact of the different like viewpoints of this the retrieval, right? But I think that for the 3D shapes, this different view is actually really important for this 2D sketch or something. So can you maybe let's say, so do you have like consider it or trying to from like which aspect to try to solve it? Because I think this is actually quite important for the sketch retrieval stuff. Yeah.
Yeah, and thank you for your question. And in this paper, due to the limitation of our data set, we cannot find the data set that one 3D shape and have different viewpoints and have several sketch image from different viewpoint. So we just ignore this question. And
yeah, okay, so but I think like if the consider is like because of like for the 3D shape, we can like render from different view, right? And
yeah.
And that has many like renders like a realistic photo, like a sketching style or something. Maybe from that you like can enrich or enhance the data sets.
Yeah, and we now try to do some experiments about the different viewpoints, and it's really important for 3D shape.
Okay, so I see. Thank you. So let's say any questions from our audience? You can either like directly ask or like also send from the chat or something.
Oh, okay.
Oh, there's a question.
Oh yeah. What kind of representation do you use for 3D shape? So I think, do you mean which network we use for 3D shape? We use a predefined network, this one, multi-wheel convolutional neural network, MVCN, which is proposed by Su et al. And we use the last representation, which is generated by this network before, and this representation is before the classifier. So I'm not sure I have answered your question.
Okay, any more questions? Okay, if not now, let's thanks again for all our 3 speakers, and also thanks to all the audience for joining us in this session. And if you have more questions to the authors, feel free to keep contact with them afterwards. So the next session is about the fabrication, which will start, I think, around the, I think will start in the 30 minutes. Enjoy. Okay, bye-bye.
Bye-bye. Thank you, Professor Huang.
Thank you. Thank you all.
Thank you.